Prepone हो गया है.
Yes. So to all the participants, we are having the first speaker with us, Dr. Rahul Prajesh from the CEERI Pilani. Let me give a brief introduction about him. Dr. Rahul Prajesh is Senior Scientist in Semiconductor Device Fabrication Group at CSIR Central Electronics Engineering Research Institute, Pilani. He received his MTech degree in Advanced Semiconductor Engineering from ACSIR, CEERI Pilani. During PhD, he worked in the area of metal oxide gas sensor at CSIR, CEERI Pilani. His research includes silicon nanowire fabrication using CMOS compatible top-down approach, microheater-based metal oxide gas sensing platforms, RTD-based temperature sensors, and biosensors. He is member of the Institute of Engineering India, member of IETE India, and senior member IEEE. He has received Young Research Award in 2021 by Institute of Engineers India. He has published around 50 papers in national and the international conferences and journals. He also has 2 patents granted to his credit. I heartily welcome you, sir, and over to you, Mike.
Thank you, Sanjuji. Thank you for this nice introduction. And today's presentation is regarding gas sensor trends. What are the technological development trends that are being followed in this particular area? I'll discuss that. So I'll share my screen now, and please let me know when the screen is visible. So I think my screen is visible now. Sanjuji, please confirm this.
Yes,
screen
sir.
is visible.
Yes, sir.
Yes, sir. You
Okay,
are
thank you, sir. Thank you so much.
Yes, sir.
So today we'll discuss about the recent trends in gas sensor technology. What are the technologies that are being used to fabricate these sensors, and what are these sensors? I'll discuss about that, and what are different components in these sensors that we'll also discuss. So I'll also try to give you some glimpse of the softwares that are being used at different stages, so that it's not boring. Then we'll discuss about, this is the outline. We'll talk about sensors. What are the important parameters related to sensors? Then what is basically a MEMS? You all know about MEMS, but I'll briefly tell you what is this. Then we'll talk about metal oxide gas sensors, which is the mostly researched type of gas sensors. Then we'll discuss about the opportunities in this particular area. What are the areas, what are the applications which you can take up for research in this technology. Before I start, I'll give you a very interesting fact. So a recent study shows that average human attention span has fallen from 12 seconds to 8 seconds. So it's very shocking data, but if you see that it is only 8 seconds. So when you if you talk about videos, it's only 2.7 minutes. So it's going to be very difficult for me to engage you for more than 1 hour. So it's 2.7 minutes only. So I hope you will be engaged in the presentation more than this. Then coming back to the topic, why we need sensors. Sensors basically are needed for different applications, but why we actually need it? Okay. So if you see this quote, which says, if you can't measure it, you can't improve it. So to improve anything, any situation, any condition, any circumstances, you first need to measure it. For example, you are having high BP like symptoms or heart attack related symptoms. You first need to measure that particular parameter so that you can take preventive measures. Okay. That's why you need sensors, just to see the exact values, and according to that, you can take the measures. For example, if you have a fever, so depending on the severity of fever, you take the dose of paracetamol, right? So that's why it is very important to measure something. If you see the market, where these sensors are being used, and if you see these two graphs, just a minute. Yeah. If you see these things, the first one is basically dependent on the applications, and if you see it's constantly increasing. The demand is constantly increasing, and if you talk about only Asia, you see that the consumption of sensor is a lot. Okay, you see it's a very huge consumption year by year. So these sensors have a big market, and research in this particular area is very important. That's why most of us are reading and working in this particular area. If you talk about sensors and discuss what is this, So the best thing to relate this is our five senses. So these are our five senses where you see you have like sight sense, hearing, touch, smell, taste, all these different five senses. These can be related to sensors at different stages, different type of sensors. Now if you talk about sensor, there is another term called transducers. What is the difference between these two? So if you see, these sensors are basically a type of transducers. We'll come back to that, but before that, I'll try to show you how we can relate sensors to our senses. Like if you see the sight sense, where we can the sense of vision, it can be correlated with camera. It's also a sensor. Sometimes it's a CCD, CMOS, different type of sensors are available. Then you have hearing, a sense which can be correlated with microphones. Then you have touch, smell, and taste, right? So these are different senses we already have, and we are trying to biomimic these type of senses using sensors. That's the perfect analogy of sensors. Now, if you talk about transducers, transducer is basically a combination of sensors and actuators. So sensors is anything which converts physical or any form of energy to electrical form of energy. On the other hand, the actuators take the electrical input and convert that into mechanical output. So if you combine these two, the sensors and actuators, that's called transducers, which convert any form of energy to another form of energy. That's basically a transducer. Then if you talk about the examples, I have already given you example of sensors, but just to reinsure that, we have another type of sensors like thermometer, thermocouple, phototransistor, microphone. So this is the mostly used example of sensors, so which is the temperature sensor. Then coming like now we understand what is a sensor basically, and then we can discuss about the different parameters of these sensors. So if you see, the first category of the parameters talks about the sensitivity and response. So these are interchangeable words used at different stages. We can also call it as response, and sometimes we call it sensitivity. If we go technically, these two are different terms, but they are used interchangeably just to minimize the confusion. What is the sensitivity? Basically, if you see, you have a characteristic curve. In characteristic curve, you have output versus input quantity, right? And you get a curve out of it. So it might be linear, it might not be linear. So in that particular case, this is your characteristic curve where you can find out the slope of the characteristic curve. So the slope of the characteristic curve will give you the sensitivity of that particular sensor. What is this basically? This is change in output with respect to change in the input. Okay. That's the sensitivity and response. Now the another important parameter is accuracy as well as precision. Just a minute. I'll just to save the bandwidth, I'll just switch off my video. I think it will be better. Yeah. So accuracy and precision, these two are important terms in sensor if you talk about the parameters. So here are four cases you see. So that's 1, 2, 3, 4 cases I've taken. So if you see this one here, all the values, all the measurements. So I talk about measurements now. All the measurements are at one place. So basically there are two things. They should be close to each other and close to center or average value. Okay. So this is our average value. That I would say is the target value. Okay. The true value. So all the measurements has average value close to the true value. That means the accuracy is good. Okay. Also, all these values are close to each other. That means they are repeatable and hence they have a very good precision. Okay. So you have to check two things. Are the values close to each other and are they close to the true value? So if they are close to true value, that means it's accurate. If they are close to each other, that means it's very precise. In the second case, if you see, the values are close to each other but away from the true value. That means it has a very big error. Okay, it's not accurate, but it is very precise. In the third case, if you see, the values are not close to each other, but the average of all the values is close to the true value. So it is accurate but not precise. In the fourth case, the average is somewhere here, so it's away from the true value, but also they are distributed in a very large span and they are not close to each other. That means it's not accurate and nor it is precise. So these are two important parameters you should understand when you go for measurements and sensor characterization. This is very important. The next I have already discussed. This is difference between measured values and actual values. Then you have linearity. Linearity is basically when you have a characteristic curve like this. So you need to find out what is the non-linearity in this particular case. Okay. There are different methods to calculate non-linearity. Just to give you a brief, you need to calculate the deviation of the actual curve with a straight line. What is the deviation? This is what is called as the linearity and non-linearity. Then you calculate the response time. Response time is basically the time taken from the initial value to 90% of the saturation value. So when you trigger something over here, so from this time T1 to 90% of the saturation value. So that's what gives you the response time. Similarly, you can calculate the recovery time. When your sensor is on recovering stage like this, from here, let's say you off the signal, switch off the signal, and this is the saturation value. So 90% of this value gives you the recovery time. Okay. So once you understand all these parameters, now you start making your sensor. What is the first step of your sensor realization? I would say the first step is the concept. You work on the concept. What is the concept? How it's going to be used? What is the application? All those things you try to answer over here. Then the second step is you try to physically, mathematically prove it for that particular concept. Okay, you try to make the proof of concept. So you make a small experiment, not the exact model, but similar to what you are trying to make. You try to make the proof of concept. So you can use mathematical model over here. You can use MATLAB like tools to validate your model is working or not. The equations you are taking are correct or not. Are you getting the correct results in that particular direction or not? And then you go for actual simulation of the device. Then you actually take the 3D or 2D model of your device, feed that into simulation tool such as COMSOL, Coventerware, and ANSYS, and apply those physics which you have already tried with the mathematical model. Those physics will be applied in that particular tool and you see the results. Okay, but simulation takes most of the times ideal conditions. You can get close to practical values, but it's very difficult to take all the conditions. Okay, then you move towards the sensor fabrication part of it. And what is the first step of fabrication? You make the layouts. Okay, how does layout looks? I'll give you a small example of that. So I have this file open. So here, if you see different colors. Okay, most of you must have worked in L-Edit and most of you have not. So those who have not worked, I'll try to explain a bit. So there are different layers in this mask, as you see. So different layers means different level of masking. Okay, so different level of lithography. So first level, let's say, is this coil. Okay, so this is the coil which we will first make. Then you have different layers. Okay, for metal electrodes, one layer may be for cavity, one layer may be for sensing layer, and there are alignment marks as well. Okay, so just to align all the things together. So once you make your device a single device, then what you do, you repeat that on the entire wafer like this. So this is the array of devices which you make on complete wafer. Then this layout goes to foundry where all the processes are done. Okay, so if you go to the next step is basically the fabrication. So in fabrication, if I talk, What are the then you go for the inspection of the device. Okay, so your device is made, then you inspect the device at different stages of fabrication. So there are inspection at microscopic level, there are inspection at electrical level. So there are different stages of inspection. Then once that device is fabricated, you go for dicing of the device, and the diced chips are then packaged into headers. Depending on your requirement, you choose a different type of header. Okay. So if I switch on the camera, I'll show you how this header looks like. So it's basically a small header. I don't think I will be able to show you. So this is a simple header which has a device mounted on it, and this has multiple legs. Okay, I'll show you in picture also, but this is the real example of a header which houses your device and which goes into the system. So coming back to the fabrication, so you have inspected your device at different levels, and you now sure that everything is correct, everything is optically looking good, and some electrical characterizations also you have done and looks fine. Then you go for dicing. You dice all the squares which you made on the wafer and put them. This is one device which goes into this header. Depending on the requirement, the header will be selected. Then you go for the system development. So this device will be integrated with your electronics, readout electronics and driver circuits, which will then convert that signal into some displayable form. So it will come on display like this much ppm of gas, this much temperature, this much sound, that will be displayed on the screen. So that's what a complete system is. That's how it's made. Now, to make these type of devices, the sensors basically, the most important technology that are being used nowadays is MEMS, which is micro electromechanical systems. So MEMS, if you go by the words, it's basically 4 words: micro electromechanical systems. Micro means small objects in the micron range. Micro is not literally micro. Sometimes you deal with size of dimensions, and sometimes some sub-micron range values also. Then the next term is electro. So it's basically related to electromechanical. You have electrical parts, some electrodes are there, some voltage is to be applied, and you see some mechanical motion or some mechanical parts are there. For example, bridge, membrane, these type of mechanical structures are there. And you call it as a system. So it's a micro system which has electromechanical parts. That's why it is called micro electromechanical systems. Then in MEMS, we cover a wide range of dimensions. So just to give you an idea, humans are in range of meters. Okay, the human hair is somewhere around 100 microns. And if you talk about these nanotechnology viruses and all, these are 100 nanometers. So just the reference. So it's a virus is 100 nanometer, human hair is 100 micron, and humans are 1 meter of a range. So in MEMS, we normally deal with 1 mm to 100 nanometers. So 100 nanometers is too low, but in some cases we do go to sub-micron ranges, but not actually 100 nanometers. So from here to here, these are the typical dimensions that are being covered by MEMS actually. Then comes the nanotechnology, where you are talking about the actually nano dimensions. Then if we talk about the application of MEMS, the very first example of MEMS is the inkjet printer micro nozzle, where you have these cavities. These cavities have ink in it, and these are connected to some actuators. Okay, so these actuators will be applied with a voltage, and with due to that voltage, there will be compression in this cavity, and this droplet will come out. So that's how it works. Okay, so this is the very initial example of MEMS. It was used earlier. Then you have more sophisticated examples of MEMS like DMD, digital micromirror device array. So what is the application? So in projectors, you may project the light at different angles with the help of these micromirrors. Okay, so that's the advantage of micromirrors. So these can be tilted at different angles depending on the So these are the actuator electrodes. So you can apply voltage on these electrodes and it will move down. If you apply voltage this side, this will move down, this will go up. So depending on the application of voltages, you can actually actuate this plate in different angles. So that means you can actually project light at different angles using the same device. So that's the advantage of DMDs. Then you have accelerometers. So accelerometers, you all know, is you have a proof mass which moves, and because of the movement of proof mass, there is a change in the capacitance, okay, or a resistance. So you measure the change in resistance or capacitance, and based on that, you tell what is the acceleration of the device or the moving object. And based on those information, you can use these accelerometer for different applications. Okay, so in different applications you are using that. So one application is the airbag deployment. So what happens when you have sudden change in the acceleration? Those airbags are deployed. Depends on the algorithms which was put in the system, but that's one application of the accelerometer. Another application is very interesting. Nowadays, you must have seen the Apple Watch 7. The ad is coming nowadays in TV. They say you have a watch in your wrist, and when you serve in tennis, okay. So just a minute, I'll switch on the. So you have a watch in your wrist, and once you go for a tennis serve, so that can actually tell you what is the speed of that serve. Okay. So that's basically is possible only because of the accelerometer, because that gives you the initial acceleration, and it's a very interesting application of the accelerometer. Now moving forward towards the application, see, another application is gyroscope. So in your phones, you must have seen when you rotate your phone, it automatically senses it is in portrait mode or landscape mode. That's basically possible because of the gyroscope, which is inbuilt in the in the phones, smartphones. Then you have pressure sensor. This is another example of MEMS, which is very interesting. These pressure sensor have variety of applications. Okay, so these can be used to measure the pressure of the gases or liquids. So if you talk about gases, one application is measuring the pressure of the tire. Okay, you fit this type of system on your tire, and it will automatically give you the tire pressure on your dashboard. Another example is a CMUT. So this is capacitively micro machine ultrasonic transducer. So this is a transducer. So that means it can be used as a source as well as detector. Okay, so it's a transducer. So if you see over here, these are the waves which are striking on the surface and coming back to the device. So it's a transmitter and it's a receiver, but both are same devices being used in different forms. Okay, so what we do over here in using CMUT, so these the acoustic waves, ultrasonic waves strike to the surface, and if there are cracks on this surface, you will have a difference in the signal. That difference in the signal will ultimately tell you what is the condition of this particular surface. So these type of devices are used to measure the structural health quality of bridges, of reactors, or those big structures where you cannot actually go and check at different places. These are the devices you can use to check the structural health monitoring. So this gives you a basic idea of what is MEMS and where it is used. But why we use MEMS? Because we can make smaller structures in this particular using this technology. So size of sensors and actuators can be very small. And if it is very small, we can make a lot of devices on the same wafer. If you see this wafer, you see this is one device. So so many devices we can make on the same wafer, which reduces the cost, time, and gives you very good yield. Okay, so that's the advantage of using MEMS. That's very important. So basically what we are doing, we are converting a sand into a sensor. And how that is done? You take sand that is converted to single crystalline silicon, and that is then processed to make different type of sensors. Okay. And how this step is done, you all know about this. So there are two techniques, Zukalski technique and float zone method. any of the method can be used to make a silicon wafer from the sand. Okay, so this is a typical process which tells you how the sand is converted to silicon. So you start with sand, which is then heated to make a metallurgical grade silicon, and most of the times this is polycrystalline silicon. Then it's again heated and processed, then you make it, so it's a polycrystalline silicon ingot. So these are the different type of cluttered kind of particles, I would say, or lumps, and then these lumps are heated again and make a very solid structure, which is then heated further, which converts that to single crystalline. So how this is happening? So there are three stages of any metal. So one is amorphous, then you have polycrystalline, and then you have single crystalline. So this is the initial stage, for example, which is sand. Then you heat it to make that polysilicon. Then you further heat it, that makes it single crystalline silicon. So that's how it is being done. So you have amorphous thing, which is converted to polycrystalline solid material, then which is further heated and a single crystal ingot is made. This is called ingot. It's a cylindrical structure which is called ingot in terms of silicon. Then this silicon ingot is diced using diamond cutters into slices. Okay, different slices, and then these slices are called as wafers. Okay, then you do the processing, chemical processing to make a polished silicon wafers. So that's what happens from sand to silicon in Czochralski technique. There may be other techniques like float zone. You can use either of the techniques depending on the application. Now, if you know what is MEMS, now it is important to understand what are the different steps to make the device. Okay. So, for example, this is approximately 12-inch wafer, which is completely processed. But what are the steps to make this type of wafer from normal wafer, plain silicon wafer to devised silicon wafer? What are the steps? So, to understand this, I'll like you to imagine a PCB substrate, PCB board. Okay, so you must have seen this type of board, which has copper, and then some tracks are there. Okay, so just remember this. That will help you understand what are the different processes in semiconductor fabrication. Okay, so I'll give you three important steps. Just remember these steps, which are the most important steps for semiconductor fabrication process. The first one is deposition. The second is patterning, and the third is etching. Okay, I'll go one by one. So you have a PCB substrate which has copper deposited on it. So first step has been done, which is deposition of the copper. Then what you do, you make pattern onto it. Okay, and then in pattern, maybe in a CAD software, by an image that is given to the computer, a pattern is given to the computer. Based on that pattern, what it will do, it will etch the unwanted copper from the undesired area. Okay, so that will be removed from that particular area. So that's called etching. So removing the unwanted material is called etching. So you have deposited, patterned, and etched. This when you get the PCB board. Okay, the same thing happens in silicon processes, where you deposit different type of layers. For example, gold, chrome, some aluminum. These type of materials you deposit. You pattern using lithography. So here you don't need lithography. You can directly write those things on the PCB nowadays. But earlier they used to do some lithography type of thing. But in semiconductor process, we still do lithography. Lithography is basically a UV source through a mask, which is also called as stencil. Okay, onto the wafer. So these light, and this has a photoresist on it. This silicon wafer has photoresist. This photoresist is light sensitive. That's why it is called photoresist. Okay, so this is light sensitive, and based on the type of your mask, the pattern will be transferred on the wafer. So this is patterning. Then the unwanted material will be removed from the wafer. That's called the etching. Okay, so these three are the important step for semiconductor device fabrication. There are other steps as well. It's not like that we have only three steps, but these three are the important processes which we mostly use. Other than these three, you have chemical mechanical planarization or polishing. You have ion implantation and diffusion for doping. And there are other steps as well, but these are the most important steps. If you only remember these three, you at least have the 80% knowledge of semiconductor fabrication process, because the deposition has like so many varieties. Okay, so it can be chemical deposition like electroplating, it can be CVD, it can be PVD. So there are n number of possibilities in deposition. So there are various possibilities in patterning also. So you have lithography. In lithography, you can have X-ray lithography, E-beam lithography, UV lithography, laser lithography. So it's like ion beam lithography. So there are n number of possibilities in this as well. Again, in etching, you have dry etching, wet etching. In dry etching, you have RI, DRI. In wet etching, you might have the chemical-based etching, the liquid-based etching, and that's also at different stages. You have bulk micromachining, surface micromachining. So these three are like three groups of lot of processes. So that's why I want you to remember this: deposition, patterning, and etching. Okay. Then we have a basic idea of the sensor. What is a sensor? Its parameters. Then we talked about MEMS. What is MEMS technology? What is sensor semiconductor fabrication technology if you use MEMS? So if you have understood that particular things, we can now move towards the gas sensor. So we'll discuss mainly about the metal oxide based gas sensors. What are the different type of gas sensor? I'll also discuss that. Okay. So just to give you the importance of gas sensors, I have collected these images from different time spans. So this is the image from Bhopal gas tragedy, you must have seen. And then there are some newspaper cuttings, which shows the detection of gas when it is leaked is very important. As soon as the gas leaks, you should have a indication which tells you that there is a gas leakage. Okay. So if you have that indication, that means you have detected the situation correctly. And if you have detected that situation correctly and at the right time, you can take the preventive measures. So that gives you the background why we need gas sensors at different stages of our life. Okay. So, and what are the application areas? If we can discuss where it can exist, where the leak can happen. So one is process control industries, where you might have gases like silane, ammonia, like that. Then you have environmental monitoring. You have COX, NOx, SOx, these type of gases. It is also used in fire detection. You measure the CO, CO2s. Then you have alcohol detection, where you measure the C2H5OH most of the times, and which is correlated to your blood alcohol concentration. Then detection of harmful gases in mines, CO, phosphine, these type of gases. Then home safety, it is another important application. So these are the different areas where the leak can happen. Okay, so that gives you a background. What is the importance of gas sensor? So there are different areas, a lot of different areas where the gas sensors are actually required. Okay. Moving towards the introduction part of it, the gas sensor is basically a device which can detect a very specific amount of concentration of gas at different locations. Okay, so there are two examples. One is this one, which shows you the dog, and another one is a canary bird. Okay, another one is a bird. So why I have put a dog over here? Because the sensory organ, the nose olfactory system is very strong compared to human nose, because it has like at least 20 times more receptors than human nose. Okay, that gives it the advantage of better sensor compared to human nose. So that's why these dogs are used. There are other advantages as well. We can discuss if required. Then you have this bird, okay, which is canary bird. Why I have shown you this? Because this was the gas sensor in 30s or 50s. People used to send these type of birds in mines, and if this bird stops singing, that means the mine is safe to go inside, and there is no hazardous gas available in the mine, and it is safe for the workers to go in. So that was the kind of sensor people used to have, at that time. Okay, so they used to send this canary bird. It makes a constant humming noise, constant singing sound, and if that sound stops or it doesn't come back, that means there is a danger in the mine and you should not go. And people also used to use a lalten type of some candle is put in the lalten. They used to insert that in the mine using some long sticks, and if the candle goes off, it doesn't keep lit, so that means there is lack of oxygen and you should not go inside. Okay, so these were the tricks people used to have used to use that time. But now we have advancement in the technology, and we can use technological electronics based technological solutions to sense the gas inside the mines. So what are the different technologies? So you have resistive gas sensors, then you have capacitive gas sensors, acoustic gas sensors, and optical gas sensors. So what we do in these technologies? So if you talk about the first technology, which is resistive gas sensor, you are actually trying to measure the change in resistance of a particular material. So as soon as there is gas on the surface, the resistance of this particular material will change, and use the help of electrodes, you will be able to measure the resistance of this particular material. Then you have capacitive gas sensors. In capacitive gas sensor, you actually measure the change in capacitance. Now, the change in capacitance might be directly due to material thickness change. Sometimes these materials have swelling effect, so the gap between electrodes will change, or the dielectric constant of the material is changing. Okay, so that will in turn change the capacitance of the material. Then you have acoustic gas sensor, where you see the resonance frequency shift. So, for example, you have a peak coming over here, and if the gas is present, so it will shift towards left or towards right. So, depending on the concentration available, you will get the shift. So, by measuring this shift, you can actually measure the concentration of the gas. Then you have optical gas sensor, which are like very like important category of these sensors, where you measure the optical parameter shift. And what are these optical parameters? It might be refractive index, it might be absorbance, reflectance. These parameters are used to measure the amount of gas present in that particular ambient. But now, for today's discussion, we have kept only the resistive gas sensor as the discussion point, because this is the mostly researched type of gas sensor and least complex out of these four. Okay, and this is easier to fabricate. The measurement circuitry is less complex compared to others, so this has more potential of being a product. That's why we are discussing the resistive gas sensors today. So if you talk about resistive gas sensor, what are the different components? We need to understand how it is made. What are the different components it consists? So the different components are micro heater. This is the first component. Then you have second component, which is sensing part. So in sensing part, we have A and B. So A is interdigital electrodes and B is the sensing film. Okay. Okay, so this is micro heater, first component, and then component is the sensing part, which consists of interdigital electrodes and sensing film. Let's visualize this thing. So you have a substrate. Now this substrate can be anything, depending on your requirement. It can be anything. Okay, anything means, so the possibility are silicon, alumina, or glass. These are the mostly used substrates we use. Some people are also trying on FR4 substrates that can also be used. Then you have the micro heater, as I told you. What is the role of this micro heater? I'll tell you in the next slides. Then you have a passivation layer, and then you have electrodes and sensing film. So as I told you, this sensing film is basically a material which changes its resistance when gas is adsorbed on the surface. So gas is coming on the surface, and due to that particular reaction, the resistance is changing. Okay, and that is being measured by the electrodes. But this reaction to happen, we need a certain temperature. That temperature is provided by the micro heaters. Okay. Now, if you go into the timeline of gas sensor, resistive gas sensor, the very first type of gas sensors were called Taguchi type gas sensors. So in Taguchi type gas sensors, what used to be done, you have a coil of maybe tungsten or nichrome wire or lanthanum wire, which works as the heater. As you see, it works as a heater. Then you have a ceramic tube. This white thing is a ceramic tube, which is coated by semiconductor metal oxide. Okay. Now you take two connections from this semiconductor metal oxides by these two leads, which helps you measure the resistance of this particular material once it is heated and gas is absorbed. Okay, so this heater provides a particular temperature for a reaction to happen, the reaction between gas and material. Okay, so at a particular temperature, this reaction will happen, and there will be a change. Because of this reaction, there will be a change in the resistance of this particular material, which will be measured by these two electrodes. Okay, so it's easy to understand. Then comes the second technology, which is basically a thick film technology. So first is Taguchi based technology, also called as tubular technology. So because you have a tube, ceramic tube, that is being used to manufacture these type of sensors. Then you have thick film technology. In thick film, you use alumina substrate, and on one side of the substrate you have heater. On the other side of the substrate, you have sensor electrodes and the sensing material. Okay, so now instead of a tube, you are using a sheet, and on one side of sheet you have sensing part. On other side of sheet you have micro heater. Okay. Now this type of technology has issues of power dissipation, too much power dissipation, because if you are using heater over here, so for example, you have temperature T at this particular point, because of too much material in between, so this temperature is required at this surface. Okay, but you have too much material in between, so there will be too much loss of the temperature. So whatever will reach over here will be T minus delta T. Now this delta T will be huge because this is a very thick substrate. That's why it is thick film technology. Then to avoid this, there comes the third approach, which is basically a planar approach, where you see you have electrodes as well as heater on the same side. Okay, but between electrodes and metal, because both are metallic in nature, both are conductors, you need to put an electrical insulating layer, and on top of that you put the semiconducting oxide. Okay, now heater and electrodes both are at the same side, so the heat will now be less consumed in the substrate. And to remove to reduce that further, what we do, we remove the material from the back side, so that the thermal mass is now less. Why I'm talking about the thermal mass? Because Joule heating is basically ms delta T. So it has m component, which is thermal mass of the material which is being heated. So when you apply a power, this complete mass will be heated. So to improve the power efficiency, you remove the material from the back side. Okay, so these are the three technologies which has been used at different stages of time in gas sensor fabrication. So just to quick revision, first was the tubular technology, where you have heater coil inside the tube, and on top of that you have metal coating, and you have two electrodes like this. Okay, then to reduce that, you have then thick film technology, which is also a planar technology, but heater and sensing part are on different sides of the substrate. In third technology, you have heater and sensing part on the same side. Also, you take the advantage of bulk micromachining and remove the material from the back side to reduce the actual thermal mass. Okay. Now, if you compare with the power consumption, so 1 has the maximum power consumption and 3 has the least power consumption, because the thermal mass is less, which gives you the advantage of MEMS. Now you can make smaller structures, smaller sensors, Also, the sensor will have less power consumption. Okay. Now, I have also already discussed the working of it. So what happens? So gas gets absorbed on the surface, and because of the temperature, specific temperature which is provided by the micro heater, there might be two reactions. One be oxidation, another one is reduction. Okay, with the surface. So if it is oxidizing, so resistance will increase in case of N-type semiconductor. Resistance will increase, and if there is a reduction, so resistance will decrease. Okay. So you now can distinguish between two type of gases. One is oxidizing gas, another one is reducing gas. In oxidizing gas, what will happen? Resistance will increase, and the amount of increase will tell you how much concentration is present. And on the other hand, if you have a reducing gas, oxidizing gas, for example, oxygen, reducing gas, let's say hydrogen. Okay, if you have a hydrogen, that means resistance will decrease, and the amount of decrease will tell you the concentration which you have exposed. Okay, hope that is clear to everyone. If you go more deep into it, the resistance change is basically related to the grain boundaries of material. So these materials are most of the times polycrystalline in nature, and polycrystalline material have grain boundaries. So at these grain boundaries, you have a barrier created. Okay, so electron is trying to move from one side to another side, but because of these boundaries, you will see some resistance. Okay, so because of this resistance, there will be a barrier potential. Okay, and once you have oxidizing nature, so what will happen? The electron will be taken from these because the oxygen will absorb at this particular point. Electrons will be taken. So what will happen? This barrier will increase. Okay, because you'll have less electrons over here, so that part has more resistance now, so this barrier will increase. On the other hand, if you have a reducing gas, let's say H2, so you will give electron to the surface because of reduction, and this will be more conducting, so it will be easier to pass that barrier, so resistance will go down. That's the basic physics of working of the metal oxide gas sensor. Okay, I'll not go into this. Now you have understood the physics, how it is working, and what is the physics of it, what is the role of micro heater, what is the role of electrodes, which electrodes are used to measure the resistance of the material. Now once you understand that, now you are ready to make your device, you are ready to design your device for different applications. Okay, so once you have those things in mind, you have understood the basics of gas sensor. What are the different parameters for to make the complete specification you should consider? Okay, so now I have divided it into three categories. One is the electrical type of specification, then physical type of specification, and then third one is the actual sensor related specifications. In electrical, what you need to check, what is the operating voltage, at what voltage you are going to operate it. Based on that, you can calculate the current. Okay, because sometimes you know the voltage, sometimes you know the power of your supply. Okay, so depending on these two values, you can calculate the voltage and current. Okay, then you should know, based on the voltage and current, you should know the maximum resistance. Okay, so if you use these two values, you'll get the maximum resistance. Now you know the maximum resistance and maximum temperature, change in temperature. You can calculate the initial resistance. How that is done? You all know that resistance is basically R naught 1 plus alpha delta T. Okay, so this is called TCR, thermal coefficient of resistance. So any material, any conductor or semiconductor changes its resistance when temperature is changed. That's true. Okay, but in some cases this alpha is positive, and in some cases alpha is negative. For example, if you talk about semiconductors, the resistance will decrease. So this alpha is negative. In metals, this is positive. So the resistance will increase. Here we are using micro heater made of metal. Okay, so the alpha will be positive, and you know how much temperature change you need. So for gas sensing application, 300 to 350 degree centigrade change is good enough. Okay, sometimes it goes to 400 degrees centigrade, but I'm taking an average case where most of the cases this is important. This temperature is important. So based on this delta T, and you know your material, so this alpha is fixed for that material, and you know the maximum value of R max, which we just calculated. So you can calculate the R naught. So you know, now you know the initial resistance of your micro heater. Now you know the resistance, initial resistance, and you also know that R is equals to rho L by A. Okay, and A is what? The width and thickness of the material, the geometry what you are making. Okay, so now you know the R, the resistivity is constant. Okay, the line width you can decide with the help of your technology available with you. Let's say we have decided 40 micron, and thickness also you need to optimize. So what is the thickness you can make at your lab? Let's say 0.2 we take the material thickness, and now based on these two values you can calculate the length, actual length of the coil. So heater is what? It's basically a coil, right? You must have seen the older heaters at your home used to be which were used to cook at homes. These type of heaters were there. So it's basically a coil. Heater is coil. So that's the same thing is being miniaturized in micro sensors. Now it's a basically coil. The more length you provide, more resistance you will get. Okay, and more dissipation of heat can be expected. Now you know what should be the length. Based on the length, you can design your geometry. What are different geometries possible? I'll come back to that. I'll come to that. Okay, so these are the different parameters. So you calculate the length. So once you have width, length, thickness, so these are physical parameters done, and then you decide what is the range of that particular sensing, gas sensing. Okay, so this range will help you decide the thickness of the sensing material. Okay, not the micro heater, but the sensing material thickness. Okay. Then you move towards the, so now you have the specification. What you will do now, you will go component by component, part by part, and check whether you have designed it correctly or not. So what is the first part of gas sensor? The gas sensor first part is micro heater. Okay, so in micro heater, I just told you it's basically a coil of metal. Coil of metal means it's basically a resistor. Okay, a metal resistor which changes its resistance when it is heated or cooled. So when temperature changes, its resistance changes. That's what is being done. On the other hand, if we give it electrical power, that power will be dissipated in terms of heat. Okay, so that gives you one idea of the micro heater design. That means it should be resistive enough. It should not be a very good conductor. It should be a resistor. Okay, it should resist the electrical flow. Then only it will convert that into heat. Then also the geometry of micro heater is important. So what are the different geometries? So you can make it like this. It is called as double spiral shape. You can make it S shape. You can make it like fan shape. Okay. So these are the different shapes which can be made. Not only these three are the shapes. There are n number of possibilities. What you can think, you can make that. Okay. Because you have it's computer designed. You can design that, put into layout, and send that to fabrication. So any design can be made. The only target of these geometries are to get the uniform temperature in the active area. So basically this is your active area. So at every point you should have same temperature. Then only your sensing film will have same temperature at all the locations. That's the target. So your geometry should be like that. It should be dense enough. The density of the coil should be very high. If it is dense, that means most probably you will have uniform temperature. So it should not be like this. So you will have blank spaces in between. So here you will have low temperature. Here you will have high temperature. That will give you gradients in the sensing film. This is not desired. Okay. So you should have dense type of geometries for micro heaters. This is also good if you have less gaps in between. It's also cover the active area. And this is also the mostly used geometry. With the help of reduced gaps, is the most used geometry. Okay, so once you have decided, as I told you, the material should be resistive enough, it should be available, cost effective, but cost is secondary because you are able to make multiple devices in the same wafer. That will reduce the cost if you are working on microstructures. So it should be resistive enough. So it can be platinum. Platinum is not a very good conductor, so it can be used. Nichrome is also resistive. Tungsten is also resistive. So any material from that can be used. But if you use nichrome, it has tendency to get oxidized. Okay. So if it is oxidized, then now the material is changed. If the material is changed, the resistance is changed. If the resistance is changed, the temperature is changed. Okay. So it's not very stable. But for crude applications, it can be used. Tungsten, on the other hand, also has tendency to oxidize, but less tendency. Okay. But for precise applications, most of the times you use platinum because it's noble material and noble metal, and it doesn't get oxidized. So the material will be stable for chemically and physically. It's stable, very stable. So if it is stable, it will give you very constant resistance, and hence you will get constant temperature for long period of time. So you have decided your material, you have decided your geometry. Then comes to the simulation. So you have all the dimensions in your mind, what material can be is to be used. Then you can go for simulations. Okay. So I'll just give you a brief demonstration, not demonstration, just a glimpse of the software, how it is done. So I have opened this console here. Okay, and I have made some geometry which I want to fabricate. So if you see this, these are the voltages, and if I go to temperature, so this is the heating part of it. Okay, that's the heating, and if you see the scale near 300, 350, that's the temperature range. Okay, so depending on the voltage you apply, so I'll show you where I have applied the voltage. If you go to the electrical currents, so this terminal shows you where you have applied the this I naught is being applied on the terminal 1. So the terminal 1 is basically this line over here. I don't know you are able to see or not. This this electrode is blue, okay, and this is black. So this blue is selected. That means as this electrode I have applied about the current, and the other electrode is ground. So this is my ground. So from here to here, the current is flowing inside this coil. So when you flow current, different voltage of current, you can see that there is a increase in temperature. As you see, the temperature is good enough, 300, 350 degrees centigrade for gas sensing application. And this is a simulation of a 3D structure. And on the back side, you see there is a cavity I have made. As I told you, you remove the material from the back side just to reduce the thermal mass. And if I increase this material, if I don't etch this, you will see a very less temperature will be increased because there will be huge thermal mass. Okay, so that's how you can do the simulation in COMSOL. If you need any help in this particular example, you can discuss with me anytime. I'll leave my email with the presentation. Okay. So coming back to the presentation, if you have doubts in this COMSOL, if you need to ask, you can ask at the end of this session. Okay. So now, what are the important things to understand to improve your simulation? So it is important to understand, like the heater, which is presented over here, is being heated with the help of Joule heating. Okay, where you apply some current, it has some resistance, and it is given for some time. This is the electrical energy. Now this electrical energy will be converted into thermal energy based on the ms delta T. Okay. Now this is the thermal mass. That's why I told you I need to remove material from the back side so that there is a good thermal efficiency. This is the specific heat. This is the change in temperature and this time. Okay. Then this electrical energy is being converted into thermal energy, but there are some losses as well. Okay. So if there are no losses, that means 100% efficiency. So that's very rare. Okay. So there are losses. Now you need to minimize these losses. So it cannot be zero, but you can minimize these losses. If you can minimize these losses, you can have very good efficiency of thermal efficiency. So what are these losses? So losses are conduction losses, convection losses, and radiation losses. Okay. So conduction losses, you all know, when two objects are in contact, then you talk about conduction losses. When you have airflow, and due to airflow, there is change in temperature. The loss of temperature is there. That's called convection losses. And when it is at higher temperature, there are radiations also. So these radiations are also lost. Okay, so that will do the radiation losses. But if you talk about lower temperatures, at that temperature, for example, 300, like that, 300, 400 degrees centigrade, radiation losses are very minimal. So you can ignore these losses, very minimal. These are the two important losses. Okay. Now, you cannot do anything about these losses because it's about the ambient. So you have you don't need to do something in the design itself. So it's the outer ambient which is affecting the convection losses. So it's the flow of air when you are testing your device. What is the flow inside the room? So that thing is controlled by the room environment, not by the sensor. So if you can control something in the sensor, that is conduction losses. Okay, and the conduction losses are basically the mass which is in contact. So basically, you need to reduce this thermal mass. That's where you can do something about the conduction losses. So that's the reason we remove material from the back to reduce the conduction losses. Okay, so this is the bulk micro machining from the back side actual device. Now, just to give you an example, I will show you these two simulations. So first simulation is this one, which has no cavity at the back side, and it gives you 30 degrees centigrade, 30 degree only, 31 degree. So initial was 27, 26, and now 31 degree. But for the same power consumption, if you see in the second case, when you make the cavity at the back side, the temperature is now around 600 degrees centigrade. So that's the advantage of reducing the conduction losses. So we just tackled the conduction losses, and now we see a very good increase in temperature. That's the advantage we can achieve with the help of conduction losses. Now in cavity also, there are different parameters you should optimize. Like I have shown you this cavity, right? Now consider you have active area, something like this. This is your active area where you have heater design. Okay, and also the sensing film in this particular area. Okay, this is the area. Now this is your cavity window. Now this cavity window size, for example, this is area 1, and the active area is active area AA. Okay. Now what should be the ratio of these two? It's also very important. Should this A1 be bigger than AA, or it should be less than AA? That you need to optimize. But most of the cases, it should be greater than the active area, because you'll have less thermal mass and you will have better efficiency. You can also optimize this with simulation. I have done some simulation regarding this, and which says somewhere around 1.5. So the cavity area is larger than the active area, and it is 1.5 times the active area. In this particular case, it should be more than that. Most of the cases, then it gets saturated. Okay, so this is the range 1.5 to 2, which you should keep for a better design. Then comes the thickness of that particular membrane from the back. So if you see, come back to this design again. Here, this is cavity, and at the bottom of this, you have silicon. Okay. Now, should you have silicon at the back or not? That is being considered in this experiment. Okay. So you have this design on the top side, and from the back, you see the image. So these are transmission images. Light is coming from the back side, and you are looking from the top side. Now here you see yellow color, but here you see white color. Now white color is because you don't have any silicon in the back side, and here you have some silicon. So because of the silicon, you are getting yellow color. But when you have no silicon left and only SiO2 layer is there, you will get the white color, because SiO2 is what? It's a glass. It's a transparent thing. Now you are getting white color. So we have done some experiments. So when we have 9 micron silicon at the back side, then we have 6, 3, 0. These are the different values we tried. And you see, when you have some silicon left, you have a temperature in 200 degrees centigrade range. But when you have no silicon left, the temperature goes to as high as 700 degrees centigrade. So that's the advantage and beauty of removing complete silicon from the back side. Of course, it will make it fragile. The device will be very fragile, so you need to handle it with very care. but it will be very power efficient. Then comes the second part of it, where you have electrodes and sensing film. So electrodes, it is important to have consider the number. So you need to consider what are how many fingers are there and what is the gap between two fingers. That's you need to understand. Okay, so most of the times the effective resistance is basically film resistance, initial film resistance divided by n square, the number of fingers square, because you have parallel resistors. You have multiple parallel resistors, so it will reduce the resistance. So that's one reason why we use interdigital electrodes. For example, you have some material and you want to measure the resistance of this particular thing using two probes. You will have some resistance. This resistance will be very high. For the semiconductors, the resistance is very high. But if you make interdigital electrodes, what happens? These electrodes have resistance in parallel, and because of the parallel combination, the net resistance will be very less compared to the initial resistance, which makes it easier to measure. In this particular case, it is difficult to measure. Okay, that's why I use interdigital electrodes. And there are other advantages of interdigital electrodes that you can read and you can discuss with me also. Now comes the sensing film. In sensing film, what are the important parameters that I will discuss? So one is the stoichiometry. Then what is the thickness? What should be the thickness? What should be the grain size? Why it is important? And what is the resistivity? Why it is important? So stoichiometry, basically you can calculate, take the help of XPS. XRD will also tell you about the which phase is present. EDX also you can do. Auger electron spectroscopy you can do. So there are different techniques to check the stoichiometry of the particular material, and you can check the stoichiometry. Are you getting the correct stoichiometry or not? For example, you want to make SNO2. Are you able to get the SNO2 or it is SNO? Okay. So you need to have correct composition, then only you'll get the best sensitivity. You need to check what is the thickness, what is the best thickness for your particular case. For example, I did some experiments and I found that the 100 to 150 nanometer is the suitable range for gas sensing application. Okay, if you see, this is a very low response, here low response, here also low response, but in between you are getting very good response over here. So these are the ranges where you should target. Okay, why you have low response in this region? It's basically a very controversial thing, because most of the cases you will see when you reduce the thickness, you will get higher sensitivity because of high surface to volume ratio. Okay, but in this particular case, I see some dip, some decline, but most probably if I go even lower, I will see saturated trend and it will not reduce further. But if you increase the thickness, it will keep on reducing. Okay, why it is that? You can think of it, and I can also discuss, like when you have a larger thickness, for example, this is the case, your gas gets absorbed on the surface. So it's a surface phenomena. Okay, so whatever change is taking place is only on the surface. So only this part, let's say, is effectively participating in the resistance change. So delta R is basically because of this area and not because of this area. But when you measure the resistance, you are measuring the resistance of complete film. Okay, and in that particular complete resistance, only this part is participating in the sensing. So if you keep on increasing the thickness, this part will keep on increasing, but this is constant. Okay, that means you are increasing the ineffective area. Okay, which reduces the response. And if you keep your sensing film within this range, you will get the maximum sensitivity. And if you reduce it further below this, what will happen? Your sensitivity will slightly reduce, and also it will get saturated very easily, because you don't have sufficient material to react and you have less material to react, and it will get saturated very easily. The third point is grain size. Okay, so what are grain size? You already know. You can use AFM and or XRD to find out the crystallite size or grain size. Okay, and these grain size are basically important, as I told you in the working of the device. You have these grains, and at the grain boundaries you get the adsorption of the gases, and because of that your there is a barrier height. This barrier height, it will either increase or decrease depending on the gas nature of the gas. It's an oxidizing gas or reducing gas. Depending on that, it will increase or decrease. Okay. Now these grain size, as I told you, so let's say you have two grains like this, and gas is getting adsorbed on the surface. For example, this is oxidizing gas. It will take away electron from the interface area. Okay, so let's say this area has depletion of electrons. So this is your depletion region. Okay, this is your depletion region. Now it will go like this. Okay, it will go like this. So everywhere from the top, the electrons will be depleted. Same is the case this. Now this dimension. Okay, so for example, this is lambda d. So twice of the lambda d here and lambda d here. If this is your grain size, let's say d, this is your grain size, then what will happen? The complete grain will be depleted or will participate in the sensing. And if it is greater than this, what will happen? Only the lambda d part will be participating in sensing, and this part is not participating in sensing, and you will not get the optimum result. So the optimum result will be attained when you have grain size somewhere in the range of twice of the lambda d. Okay, and this is called as a Debye length. So first you need to calculate what is the Debye length for your particular material and that gas combination. Based on that, you should target the grain size. Then you'll get the best response of your material. Then comes the resistivity. As I told you earlier, these are highly resistive materials, semiconductors. And to reduce that, you use interdigital electrodes. And also you can do some doping to get the resistance in your desired range. Hope this is clear to everyone. Then you go to the layout, and I already told you what are the different layers. So you have heater, pad opening, interdigital electrodes, and sensing film. The different layers are there, and these layers are designed in L-edit or tenor, what you say. So different layers are designed, and these different layers means this many levels of lithography will be done subsequently to make the complete device. And this is the sensor fabrication steps. Here you see this is the model. You have a substrate, silicon substrate. You have an isolating layer, electrical isolation layer. Then you have micro heater. These two, this is a conducting layer, and silicon is also semi-conducting. So between these two, you need to have an electrical isolation layer. Then you have interdigital electrodes, and this is also again metallic. So electrical isolation layer is required. Then you have sensing film. So this is the traditional gas sensor device made of silicon. So you make the micro heater, you pattern on that, you will make the electrodes, and you put sensing layer on the top of that, and you do backside cavity to reduce the thermal mass. So these are the different steps of gas sensor fabrication and different stages you see over here. Once that is done, then the device is kept on the header, as I have shown you. Like this is the header. On top of that, you keep the device, and then it is wire bonded onto the pins. Okay, like this. So these pins are wire bonded. Now you have 4 legs. 1, 2, 3, 4. Now you can make the connection from these 4 layers. So 1 and 3 are for heater. So you apply source here so that your heater is giving you some temperature. And then you have these electrodes where you measure the resistance of the sensing film. Okay. Then this device is interfaced with the electronics to measure the response of the device. Okay. Now you come to the characterization. Once your device is fabricated, the characterization is important. What are the different characterizations that can be done with this type of devices? First characterization is the temperature versus resistance plot, where you change the temperature and measure the resistance. Based on that, you can calculate the alpha. You remember I told you this equation, R is equals to R naught 1 plus alpha delta T. So you need to calculate this alpha first. Okay, you can take it from literature also, but experimentally you should calculate it, because sometimes what happens, the bulk material have different properties and thin films have different properties. So the alpha for bulk of platinum will be different from alpha of platinum of thin film. So that's why you should calculate the alpha first, and based on alpha you can calculate the temperature in the later case. For different powers you can calculate the temperature. You see over here 60 milliwatt is giving you 400 degrees centigrade. Then you calculate the rise time and fall time of the device, response and recovery time of the device. Here you see it's quickly heated up to temperature 430 degrees centigrade. So 25 to 430, 5.7 millisecond, and then 430 to 25, 6 milliseconds. So this is the a very fast response of the device. And then is the IR imaging. So this is the actual test of your device, of micro heater basically. So you put your device under IR imaging, and you see the you can check the uniformity. What is the uniformity of the device? As I was discussing earlier, your geometry should have uniform heating. From here you can calculate or find out what is the uniformity of the device heating, and you can also check the what is the maximum temperature you are getting. In device characterization, you check for sensing film. You go for XRD for different phases. What is the actual material you are getting? Then AFM for topology, FESIM for topology of the device, topography of the device. Then once your device is completely characterized, you go for gas sensing. In gas sensing, you have two approaches. One is a static measurement, and another is dynamic measurement. So static is what? You have a chamber. It has an inlet and outlet. Okay, you close the outlet and just input the gas inside this, and you have a sensor inside this, and you measure the resistance. Okay, this is the static measurement. Okay, once the measurement is done, you open this out and flush out the gas from the chamber. This is the static measurement. But in dynamic measurement, what happens? You have a continuous input and continuous output of the gas. Okay, so there are two measurements. In different cases, different measurements are required. So this is a complete setup where you see this is the chamber where you put the sensor. This sensor is driven by the one supply for micro heater and the measurement of sensing film resistance. This is the computerized system where you have different MFCs. So at times we can use 4 MFCs in this system. So 2 MFCs, one is for the target gas, one is for oxygen, air. Okay, so you mix different proportion of the gas to make different ppms of concentration, and you push that into the chamber, and chamber is connected with the supplies and meters. This is the like schematic of the same setup where you have this chamber. This device is connected to monitor as well as the supplies. You have a cylinder which goes inside the chamber. Okay. Now this is the typical characteristic curve of the actual device which I have plotted. Now from here, what you can extract, I can that tell you. So it's the baseline of the device, which is basically the base resistance. Okay. Once you input the gas at this particular point, it goes down. So it's basically reducing gas. If you remember the phenomena I told you, so you have reducing gas and oxidizing gas. So if you have reducing gas, the resistance will reduce. Okay. So this is the resistance drops suddenly, and then it saturates. Okay, the gas is continuously flowing and it saturates. The saturation 90% of the saturation value is somewhere here. Okay, so this from this time T1 to this point is called the response time. Okay, and from when you switch off the gas and only air is flowing, so it's the recovery starts, and this is the saturation. This is 90% of the saturation. This is your recovery time. Okay, and you can calculate the change in resistance from this point to this point. So you have this resistance and somewhere in this point. So delta R is calculated and divided by the initial resistance. That gives you the response. So you can calculate response, response time, recovery time from the same curve, and you have 3 parameters. Okay. So that's what that's how you characterize your device at the end of the characterization. Then you go for gas sensing characterization. So this is the response recovery time of a typical characteristic curve. But for actual testing, you need to check what is the operating temperature for your device. So you need to test your device at different temperatures, and you will see at somewhere around, depending on the gas and material you are taking, this operating temperature will be different. Okay, so you need to first find out this. Once you found out the operating temperature, you need to also check the response and recovery times. So response and recovery time will reduce with increasing temperature. So this is good, but you need to have a trade-off, because if you increase the resistant temperature further, in this particular case, if you see 300 degrees centigrade, so response time is and recovery time is fast, but response is low. So you need to have a trade-off between response and the times. So you can choose somewhere around these values where you get the maximum response. Then you can check the repeatability of the sensor by giving multiple pulses of the gas, and then finally you calculate what is the input concentration and what is the response you are getting, and it should be linear. Okay. So that's completes the device design, fabrication, and characterization of the complete device, complete gas sensor. Now, what are the 10 challenges in this particular technology? But the challenges are, you have a high temperature sensing, and in some cases, where the explosive some substances are available, so you cannot use high temperature sensing. So this is one advantage. Another advantage is these type of sensors are less selective. Okay, selective means if you have 1, 2, 3, 4 gases, okay, and you have a sensor, and the target gas is the second one, your sensor should only respond to the second one and not to the first, third, and fourth. That's called the selectivity. But in case of semiconductor metal oxides, it do happen that 1, 3, 4 might also give some response, not similar to this one, but it might give you some response. So that will give you sometimes a false signal. Okay, so that's called false positive. The third challenge is, you need to explore the cost-effective solutions. These are semiconductor fabrication dependent technologies, and most of the times these are costly. Effect of environmental parameters, it's also a challenge. The humidity inside the ambient changes the response, so it's also critical. So you need to consider all these challenges while making the device. I have told you all the possible parameters which are important to make that one type of device. So this applies to all sensors, not only the gas sensor, but I have taken the example of gas sensor, and this applies to all the sensors. You can take these guidelines to make any type of sensor. And what are the recent work that are being done in this particular area? One is the room temperature sensing. As I told you, high temperature sensing is not allowed at some environments. Use of nanomaterials because of the high sensitivity and selectivity. Then people are trying to explore screen printed solutions, which gives you the low cost solution for this particular type of sensors. And we can also use array of sensors. Okay, as I told you, this selectivity is a problem. But if you use array of sensors, different arrays, like I told you 1, 2, 3, 4. So what you can do, you can put 4 sensors. Just an example, you can put more. You can put 4 sensors which are more selective for gas 1. One sensor is selective for gas 1. Second number of sensor is selective to more selective to sensitive to gas 2, and sensor 3 is more sensitive towards gas number 3, and same is the case for 4. So you are getting response from 1. So what will happen? So you'll have 4 cases. Okay, so one is giving this is the characteristic for gas 1. So something like this. So this will be the characteristic for gas 2. So this should be the characteristic for gas 3, and this should be the characteristic for gas 4. So you are getting the response. This is for gas 1, gas 2, gas 3, and gas 4. Now from here, you can estimate the so you can apply classification and quantification algorithms to find out which gas is present, okay, and how much it is present. So that's the advantage of using arrays in your device system. What are the opportunities? So these type of sensors, as I told you earlier, can be used for air quality monitoring. It can be used for leak detection in various industries. Food quality assessment. This is a very a new area which is emerging where the gas sensor finds application. So as you know, most of the fruits and vegetables, they emit different type of gases at different ripening stages. And you must remember, like H2S is a rotten material smell. So once it is rotten, it will emit H2S, but at some stages it emits CO2, and in some cases there are some VOCs. Okay, so if you investigate properly at the different stages of ripening, you can estimate at what stage the currently the vegetable or fruit is. Okay, so you can actually predict the shelf life of the material. Then breath analysis for disease diagnostic. This is also a very emerging area in the gas sensor technology, where you have these biomarkers for different gases. Okay, for example, you have diabetes, you will have increased level of acetone in your breath. If you have lung disease, you will have increased level of NOx in your breath. And on the other hand, if you have renal disease, so renal means kidney disease. So if you have kidney disease, you will have increased ammonia levels in your breath. So at different stages, you will get different biomarkers in your breath. Okay, and if you can estimate the quantity, the concentration of that particular biomarker in your breath, you can actually tell about the disease. So that's these are the opportunities. Okay, so these are some facilities we have at CEERI. So we have facilities related to process and characterizations. As I told you, deposition, patterning, etching, all the process technologies we have, and also almost all the characterization technologies we have. If you need any help in that regard, you can contact me. Thank you so much. Now we can take some questions if there are any.
Should I ask a question?
Yes, definitely, yes.
Myself, Dr. Pankaj Kumar Singh from IIT BHU.
Okay.
You
Hello,
have
sir. How are you?
mentioned, thank you, sir. You have mentioned the CVD and the PVD.
Right.
Can you differentiate how this process occurs?
Oh, this is very simple. So PVD means physical vapor deposition. So these are physical techniques, and one is CVD, chemical vapor deposition. So in both, you see vapor deposition is there. Physical means you actually evaporate material physically. So you heat some material at higher temperature. What will happen? It will melt, and then it will start evaporating. And if you put something in the path of the evaporation, what will happen? The material will deposit from the target to substrate. That's the physical type of deposition. On the other hand, if you do some reaction in the chamber and the byproduct of that reaction gets deposited on the substrate, that's called chemical way of deposition. Now in CVDs, there are different technologies available like PECVD, LPCVD, APCVD. Okay, and in PVD you have sputtering, you have physical thermal vapor deposition, E-beam, electron beam evaporation. So there are different technologies available in physical as well as chemical.
That is good. One thing that we generally use the CVD, chemical vapor deposition.
Yes,
And
depends on the application. Yes.
Yes, PVD we don't use properly. Why it is happening so in such a way?
Now it depends what material you are trying to deposit. If you are targeting about the sensing film, let's say semiconductor metal oxides or dielectrics, then CVD is mostly used. But if you talk about metals like aluminum, gold, platinum, if you talk about these materials, most of the times PVD is used. So it's very difficult to use CVD for metals. So what is the material you are talking? You can, if you can, please tell me. That will help. So what is the material you are using for CVD?
Actually, we use some nanoparticles.
Exactly. So nanoparticles of what?
Gold nanoparticles and silver nanoparticles.
Right, because these are a very thin level of depositions. Then you use CVDs. For nanoparticle deposition, CVDs are preferred. But if you want to have continuous film of metals for contacts, for making tracks, metal lines, then you use PVDs, not CVDs. Like I'll give you one more example in my presentation. Just a minute. Like if you see this slide
Okay, sir. Thank you, sir.
here, this is the pattern which we have made, right? Now this pattern is very difficult. So for this pattern, we have deposited platinum. Okay. Now it will be very difficult for you to deposit platinum using CVD. So for these type of materials, we use PVD. So in PVD, you can use sputtering, you can use E-beam evaporation, or you can use thermal evaporation. But if you talk about metal sensing layer, this is sensing layer. So in sensing layer, it can be a very good idea to use CVDs. Okay.
Okay. Nice.
Yeah.
So, sir, if you possible, please share your email ID in the chat box, sir.
So it's Rahul@CEERI. Simple. Rahul@CEERI.res.in. Yeah, definitely I'll write in the chat box. Yes.
Thank you, sir.
Yes. Next question, please.
Participants can ask their questions by unmuting, or they can post on the chat box.
Sanjuji, please read the question from chat box if there are any. No, it's not there.
No, right now there's no
Okay.
question.
Mhm.
If
Any
any
other
other
participants?
participant is having any query, he can directly ask to the sir.
Pankaj, thanks for the appreciation. Vivek, thank you. And I'll also leave my email ID in the chat box.
Yeah, yes.
I've tried to cover the complete sensor fabrication, complete sensor development approach, which includes the design, fabrication, and the characterization of the device. So if any section you have doubt, please tell us.
Thank you so much, sir, for such a nice presentation and all the information we have get about the gas sensors. And
Thank you.
hopefully we will meet soon after the pandemic. If it's over, then in person we will have some session with you.
Definitely, Sanjay. Thank you so much.
Yeah, thank you so much,
Thank
sir.
you.